Okay, page 19 of the scheduling notes. So the question was, what happens when task 3 reaches the end of its time slice? So how does a context switch work with fixed priority preemptive scheduling? So similar to the round robin, we're going to want to enqueue the running task at the end of a queue, and the question is which queue? Well, task 3 has priority 5, so it would go at the end of Q5 because that's for priority 5 tasks. And then we need to dequeue from that queue, and that will give us task 4, which we will then set as the running task. So for a context switch, there are 2 steps. So we want to enqueue the running task at end of its priority queue. So for task 3 again, that was Q5 because it was priority 5. And the scheduler knows that because it has a pointer to the running task, so it can read its priority. And then dequeue next task to run from the same queue. So if there's only one task at that priority level, on the context switch it gets enqueued and dequeued, so basically it just keeps running. Otherwise there will be other tasks running. Now when you want to add a task, say it's become unblocked or you created a new task, you just enqueue it at the end of one of these queues, and which queue is just based on its priority. So enqueuing a new task is order 1, and I'll put new in brackets. It can be just a task that was blocked and becomes unblocked. Dequeuing is a bit more complex. Because if you're, so let's just say that a task is terminated and you want to remove it from the queue. That's fine. It's doubly linked. You can remove it in order 1. So let's just say can remove from the doubly linked queue, and that's going to be order 1. But what if you empty that queue? What happens? So just say in our example that the priority 5 queue empties because all 3 tasks, tasks 3, 4, and 5, all become blocked on something or a variety of things. How does your scheduler pick the next task to run in that instance? And we know that it should be picking one of the priority 2 tasks because we can look at that diagram and see that. So next should be task 1. So if the priority queue empties, then we must find the next non-empty queue. So we must find the next lowest non-empty queue. And so our options, option A is just to do a linear scan. So we were at priority 5, so just check priority 4, priority 3, and then we'll find it at priority 2. So a linear scan for the next non-empty queue. And you'll always have a non-empty queue because you've always got the idle task. What is the runtime complexity of this operation? And remember, this is worst case. So in the worst case, you had a priority 7, highest priority task. That task blocked, that queue empties. And in the worst case, the only other task that's ready is the idle task. So you're going to scan all the way from task 7 to task 0. So that's order n. And that's not a good number in scheduling. You want your scheduler to run in order 1 or maybe order log n or something. So there is a trick that is used. So the trick is to use a bit vector to represent the that's a non-empty, that's an M there, the non-empty queues. And so in our example, we have 8 priority levels. So this bit vector would have 8 bits. It could fit in a UN8 type. And each bit represents a priority level. If that priority level has a non-empty queue, there will be a 1. So we had the idle task in priority queue 0. We had 2 tasks in priority queue 2. And in our example, we had a couple tasks, 3 tasks at priority level 5. And the others are empty, so they'll have zeros. 1, so 1 indicates that Q0 is non-empty. So how does that help us? It turns out that most processors have an instruction that lets you count the number of leading zeros in a bit vector. So how many leading zeros from the most significant bit do we have here? We've got 2. So if you can count that with one machine instruction, and you know that you've got priority 0 to 7, you can do 7 minus the count of the leading zeros, 2, and that will tell you that priority 5 is non-empty. Or if priority 5 empties and you've got all zeros except for Q2 and Q1, count leading zeros will return 5, because 7, 6, 5, 4, 3 will all be zeros. A machine instruction can count the number of leading zeros. So for example, with ARM, it is the CLZ instruction, count leading zeros. So that's one option. If your processor does not have such an instruction, there is an algorithm that can do this in order 1 time. It uses lookup tables and some bit shifting and a couple logic operations, a logical and, no, a bitwise and a bitwise not. So can also be done in software with the Debrusion, not sure how you say that. It kind of sounds Dutch maybe, I'm not sure. With the Debrusion numbers algorithm. And there's this really elegant paper from MIT in the 70s describing this algorithm, but now most machines have such an instruction. So the in both cases, we can find the next non-empty queue in order 1 time. And as a result, fixed priority preemptive scheduler overhead is order 1. Now we've added a bit of bookkeeping that's required. We've got to maintain this bit vector too, but that's just a few instructions. And as a result, fixed priority preemptive scheduling is widely used. So FPP is widely used. So any commercial real-time operating system like VxWorks, FreeRTOS. I don't know if I'd call that commercial, but it's very popular. It's used in industry, so sure, let's call it commercial. Or QNX, which is now owned by Research in Motion, or whatever they call themselves now. All use fixed priority preemptive scheduling. So what's the drawback here? So limitation. There are no deadlines. And as I keep saying, this is a natural expression for real-time operating systems. Events happen, you respond within a certain amount of time. So that's the main drawback. Now we can approximate deadlines with priorities. And how, you might ask? Well, that's going to be on the next page. It's called rate monotonic scheduling. And there's one other drawback, so there's actually two. So limitations is that you can have frequent context switches, because it's based on the idea of a time slice and you keep switching.